Hello everyone. In this video, we are going to look at an interesting topic, transforming probability distribution functions or PDFs. What does that mean? Well, as you know, and I talked in some of my previous videos, it is very common and not very difficult to generate data from a uniform distribution, right? So I explained different algorithms for it and how something like in MATLAB or Python, they generate random numbers. But these random numbers that are generated, they are typically uniformly distributed within a range. So most of the time between 0 to 1, right? With a command like rand in MATLAB or in Python, if you have the numpy random.rand will generate a number from a uniform PDF in range 0 to 1. But now the question is, when you generate random numbers from other distributions in MATLAB or NumPy or anywhere, how does it do that, right? How would you generate numbers from a Gaussian distribution or an exponential one or a Cauchy one or any other one, right? How would you do that? And the answer is one very common way to do it is by transforming PDFs. What does that mean? Means I generate my numbers initially by a uniform distribution in range 0 to 1, and then I transform these numbers using some function, nonlinear function, such that the distribution of these transform numbers is, for instance, Gaussian or exponential. The question is, what kind of nonlinear function would you use to make this transformation? Okay, so here I have variable x, and I transform it to some new variable, right? Some, whatever you want to call it, x prime maybe. This one is a uniform distribution. This one may be a Gaussian distribution or exponential distribution or anything like that. The question is, what kind of f of x do I use? And the answer is actually it is the inverse CDF of the desired distribution. So if it's Gaussian, inverse cumulative distribution function of Gaussian, or inverse cumulative distribution function of exponential. So the inverse CDF of the desired distribution is the answer. Now, you might say, first of all, what is that? How would you calculate it? And why this function works, right? You're just claiming something. Show me, prove it, right? That's right. You have the right to ask that question. So let's see. First of all, this is one of the places that the cumulative distribution function has application, right? Because if you watch, for instance, my previous videos that I showed you different probabilities, PDFs, and then for each PDF, I also plotted for you the CDF, the cumulative one. You might say, what's the application of cumulative? Well, there are lots of applications, but here is one important one. First of all, what is the cumulative distribution function? What's the definition of that? If you haven't seen it already, it is the integral from negative infinity to x of the PDF, that's your PDF function, versus the variable. And this is basically the chance that here your x, this x, is less than or equal this one. Okay, so the chance that your random variable is less than or equal some amount, that is the cumulative one, right? For instance, in Gaussian distribution, right? If my x is here, let's say one standard deviation away from the average, so this is mu plus sigma, this is my small x, and this axis here is this x, and this is f of x, then basically it is the area from negative infinity to x. So all of this area up to this point, that is the cumulative distribution function for that specific value. The area under the curve, which is chance of being less than that number. Of course, it's less than 1 because the whole area is 1. So if you find the inverse of this function, first you have to calculate this cumulative for any desired, and then you have to find the inverse of it. And if the inverse exists, then you can use it to go to this desired distribution. So now it is time to show why this inverse cumulative is working. So if I call the inverse cumulative fx inverse of u, okay, this is my inverse function. Now if I apply that here, right, if I use it right there, why does it work? Let's see. So here we want to look at the cumulative distribution function of this transform variable. This x that you see in here, that's corresponding to our x prime up there. So if we want to see, we claim that this guy here, this x prime, is going to be the distribution of that is going to be my desired distribution. Well, how can you check it? Here we're going to check the CDF of this transform variable. So we say the CDF of this variable is going to be what? It is going to be the chance that this x is less than some given x, and for that capital X now, the variable, we replace it by fx inverse of u. This is less than this. Now here we make a claim. We say this probability is the same as this one. And now if you look at this one, this is exactly what? Based on this definition that we had, right? Look at this. Exactly based on that definition, that is the definition of cumulative of f of x. So here I showed that the distribution of the transform variable is the same as the CDF of the original one. So this is the CDF of x. And that is exactly what I want. This is the desired one. They are the same. So my new variable cumulative function is the same as the one that I want to be. So there we go. I have it. But the question is, when you go from this left side to right side here, why these two are the same, right? This f inverse of u less than x is the same as u less than fx of x. Where would you get that from? Okay. So, in order to get this, here we are using two important properties of the cumulative function. What are they? One, first of all, we assume that it has inverse, so this guy exists. Second of all, you know that the cumulative function is an increasing function, correct? So if you get x1 and x2, where x1 is bigger than x2, then the CDF of x1 is also bigger than CDF of x2. Why? Because x2, that means x2 is to the right side of x1. So if this is x1 and this is x2, x2 is to the right side of x1. So the cumulative for x2 not only involves the area from negative infinity all the way to x1, but also includes this extra green portion. And this area is positive. Okay, and remember that your PDF function is always positive, so area under the curve of it, this portion is always positive, so this is an increasing function, okay? Because of that, well, how can I use this property that I just explained? Well, let's see. So look at here. Oh, sorry. Remember what we need to prove. We need to prove this guy. So here we start with this. Yes? This is similar to saying x1 is less than x2. Okay? Something is less than something else. Now, because x1 is less than x2 implies that f of x1, and f here is the cumulative function, f of x of this, because x1 is less than or equal to x2, then f, capital F of x1 is also less than or equal capital F of x2. So we apply capital F to them, so you get this. And you know f and f inverse are basically canceling each other, so the result of that simply is going to be u less than or equal f of x. And look at this, that's exactly this one. You see, so we started from the left side and we ended up with the right side. And when these two are the same, then we can apply the probability function on both sides as well, because that's exactly the definition of probabilities. And then guess what? Here. So I showed that the distribution of this new variable, CDF of the new variable, is the desired CDF. Therefore, this transformation should work. Now, you might still not believe it until I show you that in practice. So first, let me show you that in practice, and then we come back and talk about finding this F inverse, because that's an important thing. So here, let me first show you a demo. So what is the demo here? The demo is here, I generate 10,000 numbers from a uniform distribution between 0 and 1, okay? Then what do? First, I find the function, the inverse CDF function of exponential, and I apply that function to this u variable. So this is that function, this is the inverse of exponential. I apply it to the u variable, and this new guy, x exponential, should actually, if I plot the histogram of u and the x exponential, should show something like real exponential histogram or PDF, right? Then I do it for the normal distribution. So I apply this inverse CDF of normal distribution, for which there is a function in MATLAB, norm_inv. I apply that to u with the same mu and sigma of 0 and 1, because I want to transform it to 0 and 1. And I get x norm. So this x norm should ideally behave like a Gaussian distribution. And I do the histogram of that as well. So look here, if I go ahead and run this first section for you, I want you to see what happens, okay? Whether what we claimed is actually working or not. There we go, look. This is the original variable, 10,000 numbers between 0 and 1. You see it's almost uniform. Of course, you never get it perfectly uniform, but 10,000 is relatively good number. Now look at the x exponential. Look at the distribution of that. It's absolutely exponential. And look at the other one, x norm. It's absolutely behaving like a normal variable. Now I can get this better by adding more numbers. Instead of 10,000, go ahead with 100,000, with 1 million, and so on. It takes a little bit more time, but guess what? Absolutely, you see they are behaving. And you can do that for any other distribution. Start from uniform and go to any other one that you desire. All you need to find is CDF inverse of that desire. Now, let's take a look at these two examples. So what is the CDF inverse of exponential? So for the exponential, the PDF function is lambda e to the negative lambda x. So what is CDF? CDF is going to be clearly the integral of PDF from negative infinity to x. So this is going to be from negative infinity to x of lambda e to the negative lambda t dt. And I bet everybody can do this integration, correct? Because this is just going to be negative e to the negative lambda t, correct? If you take derivative of that, that's exactly this guy. And then you calculate this at x and infinity, negative infinity, right? So what would you get? Now, one thing that you have to pay attention to, because you might say, well, this is going to be infinity. You are right. But here, we did not use one important property. In exponential distribution, x should always be positive. It can never go to negative infinity. So actually, this initial condition cannot go to negative infinity. You have to start from 0. Okay? Look. So now it is going to be what? Negative e to the negative lambda x, and then at 0 it is 1, so it is going to be 1 minus e to the negative lambda x, and that is exactly this guy. So we found the CDF, now we have to invert it. So if I call this, for instance, variable u, how do I find for x? Well, here I take the two sides and switch them. So you will get e to the negative lambda x. It is going to be 1 minus u. Now you take a natural log from both sides, and x is going to be negative 1 over lambda natural log of 1 minus u. Look, this is your inverse function, which is exactly this guy. So this is my inverse CDF. If I apply this, that should give me an exponential. Now, one thing important here is you can simplify this if you want to, correct? Remember, your u is in the range 0 to 1. Your u is in the range 0 to 1, so 1 minus u and u are behaving the same way, correct? They are both between 0 to 1. If u is between 0 to 1, 1 minus u is also between 0 to 1. So if you want, you can use this function instead. Just a little bit simpler. But you can use either one. And here, you see, it's that first one that is used, actually. And it is absolutely working. Good. So we use this one exactly in that MATLAB code. We did not even go for this. Now, what about the normal distribution? You might say, can I find this inverse for any desired distribution? The answer is not analytically always. Sometimes for some distributions, the inverse does not exist. Okay, you have to do it numerically. Even the CDF itself might not exist analytically. Forget about this inverse. Really? Like what distribution? Well, normal distribution. In normal distribution, the CDF of x, okay, capital F, is integral from negative infinity to x of what? 1 over square root 2 pi sigma squared e to the negative x minus mu squared over 2 sigma squared. So now this is going to be dt, and I have to change that x also to t, or this one. So it's going to be t minus mu squared, right? And guess what? This integral does not exist. There is no definite integral for this. You can calculate this through numerical calculation. So for each x, you can numerically calculate that integral, but there is no analytic function for it. So if I call this phi, if I call this f in here, we call it the phi function. Then because phi does not exist, phi inverse does not exist, but numerically we can get all of them. So here, to invert it, this phi inverse function, we can only do it from lookup tables or numerical calculations. And in softwares, there are functions for that. In MATLAB, the function that you just saw, it was norm_inv, okay? Inverse of norm, and inverse of what of norm? CDF of norm, not PDF of norm. Okay, so that function exists. And in Python, it comes from the SciPy library, scipy.stat.norm.ppf. Okay, by the way, this phi inverse of CDF of normal distribution, it has a name. We call it the quantile function or probit function. But quantile is more common. So if somebody says we need to use the quantile function here, then that's exactly what you have. Okay, so here we do it numerically, and guess what? That is exactly what you can see here, and we got the two distributions that we wanted, right? So here we go, and we can do that for any other one as long as we can find it analytically, or we have a numerical or lookup table for the inverse CDF. We are good to go. And if you remember my previous video, let's see if I have that. You see, these are the PDFs for all different functions. So all you need is to do the inverse of them if you can. I mean, not all of them are easy. Okay, you can see that here, right? That you have to basically do some integrals just to get the CDF and then see if you can invert it. But in general, whether numerical or analytic, this is possible. Now, one other thing I want to mention, which is more interesting, So here we went from a uniform distribution to desired. Sometimes we need to do the exact opposite. We have an arbitrary distribution, we have to turn it back to uniform. Really? Why would you do that? Well, one application is in image processing. It is called histogram equalization. And I have a separate video on that under playlist image processing and computer vision. I explained that, but not individually. There is this video, let me show you. It's called gray level adjustment or gray level transformations. This one here. And here at the end of the video, I talked about histogram equalization. Okay. But I also have this video under the same playlist where I showed how to do histogram equalization in OpenCV. But the theory behind histogram equalization is what I'm about to tell you. So what is it? So if you have any image, okay, it has some histogram of gray level values or intensities, correct? So if you look at a grayscale image, then you'll see that each pixel has some intensities, and these intensities could be from 0 to 255, or you can scale them down, normalize them to be between 0 to 1, where 1 means very bright, basically white, and 0 means the black pixel, and shades of gray between them. So if you look at the histogram of any image, right, let's say this is 0 or 1 or 0 to 55, well, you get some bars, something like this. So for instance, if my image looks something like this, that means you have a lot more black pixels and dark pixels than bright pixels. So the image is overall a dark image. Or on the other hand, if you have a lot bigger frequencies in the bright region, but you have some small things here, that means your image is very bright. It has a lot more bright pixels. Okay? Yes? Or you can have, for instance, a non-uniform distribution. So the pixels are only concentrated around some specific region. So something like this. And then the rest of it is not so good. This is what we call a low contrast image. So your pixels are only around some specific shades of gray and not all over the place. So this is what we call a low contrast image. If you want to get a high contrast image, you have to change this to a histogram where between 0 to 1, you have almost equal distribution of light intensities. That is a high contrast image. Okay, because in all shades of gray, you have some intensity, but here you only have it for some specific values. So when you want to improve the contrast of the image and sharpen the image, one way is to convert this arbitrary initial histogram, which could not even necessarily follow any of the functions we learned, this arbitrary PDF, we want to convert it to a uniform PDF. Okay, and how do we do that? Well, probably from what we learned initially, remember, if I want to go from arbitrary PDF to, if I want to go from uniform PDF to arbitrary PDF, what transformation function did we use? We use the inverse CDF of the desired, What about here? Here we are doing the opposite of that. So what kind of function should I apply to this? To this arbitrary one? Exactly, the CDF itself. If I apply the CDF of this PDF, if I apply the CDF of it to this, then I go from arbitrary X to the uniform U. All I need is to find the CDF of this histogram and apply it. And then you might say, well, this is not a well-known function, right? This is not a well-known function. How would you find the CDF for it? Because here, look, we had a function for PDF. We used this integral to find CDF and then invert it or anything. But here, we don't have a function for this. We just have a bunch of numbers. How would you find this function? Well, you have to find this function also numerically and treat it like a lookup table. How? So you start from the original intensities between 0 to 1, column R. Now, if the new equalized intensity levels are S, so you go from R to S instead of X to U, right? The function that you need to use here, as I said, is gonna be the CDF of the R. This is the function that you need to use. Now, how would you form the CDF? First, you calculate the histogram of this original data. Well, here you have some histogram. Now, in order to convert this histogram to approximate a PDF, we have to normalize it. So we divide these histogram bars, the value of these bars, by m times n. What is m times n? The total number of pixels. So what does that do? It makes sure that when you normalize it in this step, it still looks like a histogram that it used to be, but it normalizes that. So now the area under the curve of this over the whole range is equal to 1. Okay? Here it might not be 1, but here we divide it by m times n. So when you integrate that, this whole thing becomes 1. So now this histogram by normalization can approximate my PDF. Then to find CDF, all we need is for any point, we just add the previous frequency. So if I want to know what's the CDF at this point, right? If I need to know CDF at this point is how much, all I need is to add this bar and all of the previous bars, all of these frequencies to it. That is going to be the CDF here. If I want it at this point, I need to add the frequency at that point plus all of the previous frequencies. Okay, and that should give me the CDF. And once you have CDF as a numerical bar, so now when you do that, now you get, for instance, something like this. For instance, now of course it's an increasing function, but let's say here you stop right there, right? So now for each point, you have the value of CDF for it, and guess what? Now that you have it, you just go and apply that transformation to it. So now in this S domain, guess what? You have your uniform distribution. And if you want to make it like a uint8 image, you can multiply it by 255 and round it. And that is exactly what you do in histogram equalization. So here, look, in the second part of this code, I browse for an image and I read an image that is low contrast. Then I'm going to use the histequal command in MATLAB, which does all of this operation basically for you. And guess what? I show the resulting histogram and I show you the resulting image. Okay, so let's go ahead and do that. So here we go. We read the image. Look, this is the original image. You see only specific shades of gray, very low contrast. This is the distribution of that, only between like 100 to 200. This is the resulting distribution. It's not perfectly uniform, but you see it's all over the place. You have now values below 100, more than 200. You have it all over the place, close to each other almost. And look at the resulting image. Much, much better contrast and nicer image to look than this one does. And all we did to go from here to here, we found the CDF of this and we applied it. That's all it is. That's all this histogram equalization command does in MATLAB, okay? I don't know if I can show you the details of that. Let me see if I can open it for you and show you the result of that. But there we go. But basically, all this function does is exactly the same thing, okay? So if you go and look into this, of course, initially you have lots of checks and everything, right? But then you see here, look, you're normalizing the histogram first to make it a PDF. And then from that PDF, you calculate the cumulative histogram, the CDF function. And once you have the CDF function, now you apply that. And once you apply it, you get your results. Okay? So of course, instead of all of these lines of code, you can only have some few lines of code, but that function is written so it can handle our errors. Okay, so I guess you learned how to go from uniform to arbitrary and from arbitrary to uniform, and what are the applications for them in different places. And I'll give you access to this file so you can basically work with it and learn from it. And thank you so much for your attention.